Have you ever stopped to think about how Google Maps, or really any map app, actually works? I mean, you plug in a destination, and in seconds, it sifts through millions of possible roads to find you the absolute fastest route. It feels like magic, right? Well, it's not magic. It's some seriously brilliant computer science. So let's pull back the curtain and see exactly how it works.
So what is the secret? I mean, think about the sheer number of possible ways you could drive across a city. How does it nail the best one every single time and do it faster than you can even buckle your seatbelt?
You might think the answer is some bleeding-edge AI or a quantum computer, but you'd be wrong. The core idea, the foundational concept, comes from way back in 1959. It's a beautiful, elegant algorithm thought up by a Dutch computer scientist named Edsger Dijkstra.
And yep, that secret is Dijkstra's algorithm. Now, to be clear, modern systems like Google Maps use supercharged, heavily modified versions of this. But Dijkstra's original idea? It's the engine. It's the fundamental building block that makes the whole thing possible.
So what does this algorithm actually do? Well, in tech speak, it solves the single source shortest path problem. All that means is it finds the fastest way from one starting point to every other possible point in a network. But there's one really important rule it has to play by. The cost to get from point A to point B, what we call an edge weight, can't be negative. And for finding a route, that makes perfect sense, right? You can't have negative travel time. And here's the really cool part. The genius of Dijkstra's algorithm isn't that it's super complicated. It's the opposite. It's based on a really simple, almost obvious idea. It's what's known as a greedy algorithm.
To get what we're talking about, just picture a city map. Every single intersection, that's a node. The roads connecting them, those are edges. And each of those edges has a weight, which is just the time it takes to drive down that road. This is the perfect way to visualize the puzzle we're trying to solve.
Okay, so what on earth does greedy mean here? It means that at every single step, the algorithm makes the choice that looks best right now, without worrying about the big picture. It's incredibly short-sighted, but in a really smart way.
So back to our map. What this means is that it always explores from the intersection it can get to the fastest from the start. You could almost say it's an optimist. It's always betting that taking the shortest possible next step is going to lead to the shortest overall trip in the end.
So, how does this greedy approach of always just picking the closest spot actually work without getting lost? Let's walk through the core logic, step by step.
Okay, here's the game plan. First, you initialize everything. You say your starting point has a distance of 0, and every other spot is basically infinity far away. Then the loop starts. You select the unvisited spot with the smallest known distance. You finalize it or settle it, which means you've now found the absolute fastest path to that spot, and you lock it in. Then you look at all its neighbors and relax them. That's just a fancy word for asking, hey, if I go through the spot I just locked in, can I get to you, the neighbor, any faster? If the answer is yes, you update its distance. And then you just repeat that over and over. Select, settle, relax, until every intersection you can reach is finalized. So the logic totally makes sense. But when you're dealing with a map of New York City or London with millions of intersections, running that loop efficiently is everything. Which brings us to a really important question.
Right. At every single step of that loop, how do we instantly find that one unvisited intersection with the smallest distance, out of potentially millions of options? The answer isn't about the logic, it's about using the right tool for the job.
I mean, you could just keep a giant list and scan through the whole thing, every single time. But that would be painfully slow. Road networks are what we call sparse, which just means most intersections are only connected to a few other streets. For this kind of setup, a supercluster data structure called a binary heap is the perfect tool. It's specifically designed to always keep the closest options right at the top, making them incredibly fast to find.
And by using that binary heap, the algorithm gets incredibly efficient. Now, for you computer science folks, that gives us a time complexity of O of E log V, where E is the number of roads and V is intersections. But here's what that really means for the rest of us. It's fast enough to work on massive real-world maps without making you wait.
And what about computer memory? Well, the space it needs grows pretty reasonably. It's directly proportional to the number of intersections. We just need a little bit of space to keep track of the distances, the path back to the start, which spots we've already finalized, and which ones are still in the running. It's actually surprisingly lean.
Okay, so let's bring this back to the real world, because as powerful as this algorithm is, it has one major Achilles heel, and real systems have to use some clever tricks to get around it and to squeeze out even more speed.
So what's the catch?
Well, while it's basically foolproof for problems like travel time, there is one very specific scenario where its greedy logic totally breaks down, where it will confidently give you the wrong answer.
And that scenario is called negative weights. Imagine a road that actually gave you time back, like a teleporter that sends you back in time a few minutes. If that existed, Dijkstra's whole approach of lock in the closest thing would completely fall apart. For those weird kinds of problems, you need a different algorithm, like Bellman-Ford. It's slower, for sure, but it can handle those negative costs. It's a classic trade-off between speed and power.
And of course, real-world systems use all kinds of awesome optimizations. The A-star algorithm, for instance, is like Dijkstra's with a built-in compass. It uses an educated guess, a heuristic, to steer the search toward your destination instead of just exploring everywhere. Or there's bidirectional search, which is so smart. It searches from your start point and your destination at the same time, hoping to meet in the middle. That simple trick drastically cuts down the search area and makes things way faster.
So let's wrap this up. If you remember 3 things from all this, make it these. First, the core idea is that simple, greedy choice. Always explore the closest spot first. Second, that strategy only works if your paths can't have a negative cost. And finally, its incredible speed in the real world is all thanks to using the right data structure, like a binary heap.
And that leaves us with one last thought. All those advanced algorithms we just mentioned, A-star, bidirectional search, all of them, they aren't replacements for Dijkstra's. They are brilliant enhancements that are built on top of Dijkstra's fundamental greedy logic. So understanding this one, simple, elegant idea from over 60 years ago, it's still the key to understanding how our modern digital world finds its way.